Hello students, welcome back. We completed up to section 4, but before starting section 5, let's have a brief recap. In section 0, we had a review on a long time ago topic. Most students must have skipped it. Section 1, we had a foundation of everything, and that had some depth. We went through general equations which can create either a curve or several curves. We considered a condition whether a point is on a curve or not, intercept problems, symmetry problems, those kind of things. Yes, those are important. They have necessary foundation for all, and also they have some depth. But otherwise, we didn't have anything in depth. Section 2, just use of technology. Yeah, you can get used to those quickly. Need some time and exercises. Section 3, not really worthy of any of our class time. Section 4, worthy of only minimal amount of class time. Section 5, alright, this is a real deal, but even so, we went through very little. We went through just simple variations, direct and inverse variations, and nothing more. Just variation between two quantities. Now what if we consider truly multivariable variation? Sometimes more than two quantities are linked together through a variation of relations. For instance, if the quantity z varies directly with u, varies directly with v squared, varies inversely with x, and varies inversely with y cubed, then you're going to get this kind of relation. This is a variational relation, so no addition or subtraction. If there were, then that should be one quantity with parentheses there. And then direct variations are the numerator, inverse variations are the denominators, multiplication and division respectively, and then u and v squared, direct, x and y cubed, inverse, kind of like that. And as usual, we have a variational constant. Now, how do you do this? In this kind of problem, we really have to use those standards method, the 4-step method. Here's an example. The strength S of a rectangular beam of wood varies jointly as the width W and the square of the depth D, and inversely as the length L of the beam. Suppose that the strength is 90 units when the width is 2.5, D is 1.5, the depth, and L is 14.0. Find the strength S when W is 1.5, D is 2.5, and L is same as before, 14.0. Basically, we are looking at this situation. This information is given, and same piece of plank, just tilt it and create this. What do you expect? Yes, this will be stronger. Put some weight in the middle, put weight in the middle. This will be stronger because we have more depth compared with width. Length is the same, so that's not going to contribute. So how are we going to do that? Well, we'll have to use that 4-step process as a matter of fact. Let's go ahead and do that. So let's put the variation equation, or more precisely speaking, provisionally variation equation, provisional variation equation, temporary variation equation. How does it go? Strength is proportional to, yeah, always we need variation constant. Without k, you don't get anything. And varies with W and D squared, but inversely with L, like this. L is a little bit hard to see. Let's use capital L here. I don't like this very much either. Let's put L downstairs. Okay, that's better, but we have a fraction, so let's use bigger font. even bigger. I think I got a bit overboard. Okay, alright, keep it like that. And that's my variation equation, but it's only provisionally. Why? We don't know the k value, so this is not complete. Alright, let's go to step 2 and let's find k. Let's find this variation constant k. How do you find it? Well, let's see. The strength is 90 units when the width is 2.5 and depth is 1.5, and that should be squared, and length is 14.0. From here we have to find k. Well, that's easy. Flip this denominator to the other side. 90 was there before, and then multiply 14.0, and then divide those in numerator. 2.5, 1.5 squared. What is this quantity? And you can punch this into calculator. No big deal. I have a calculator here, so let's use it. I'm getting 224. That's my proportional constant. So now that I got this proportional constant completely identified, I can put it back to this provisional equation to get completed equation. Step 3. Completed variation equation. So that's the equation, right? But in place of k, we have now definite number 224 goes in there. Well, there's no reason to emphasize in different color, so let's just keep it that way. Okay, we got the equation. So let's answer the question. Find S when W, D, and L are like those. Okay, alright, no problem. Copy and paste this thing. And W is 1.5. D is 2.5. And then L is 14.0. And calculating this, no big deal again. Put it into calculator and run it. Ooh, this multiplication symbol here, Mathematica didn't like it. 150. So the strength is 150. Previously 90. After tilting we get 150. Definitely it got stronger. Let's go back to the picture again. This one had strength 90. So in the middle we put some weight and then how much it can bear, versus this one here tilted, we have more depth, as you can see. What did I do in my answer key here? Get the variation equation, okay, alright, and find k. Put the numbers in and find k, step 3. Put k values back into the first equation to get the completed variation equation. This one is just provisionally. We don't know the k value. Now we know, and this is complete. And then with the completed equation, we answer the problem. Okay, remember the 4-step process. Let's see, do we have time for another problem? Probably not. So I'll just show you the background and then I'll ask you to complete the problem. Okay, this is based upon real experiment by, this is really famous experiment by Henry Cavendish. It is known that the gravitational attraction force F between two objects varies jointly to the masses m1 and m2 of the objects, and inversely to the square of the distance r between the objects. So how do you write this as a variation? Oh my, sorry about that. Okay, all right, I got it back luckily. So proportional constant k times m1 times m2. These are direct variations. It says varies jointly, does not specify whether it's direct or inverse. That means it's direct variation. If it is inverse variation, it must be specified. Inversely to square of the distance, so r squared goes down here. Let's take a little bit bigger font. And traditionally, instead of k, we use capital G for this constant, and we call it the gravitational constant. And this thing is typically known as Newton's law of universal gravitation. Very, very famous equation. Perhaps it should be the most famous equation ever, at least in my opinion. Above that E equals to mc squared equation, which is I think more widely known these days to most people, but I think this one tops it, in my opinion. Okay, that's a variation equation. And then from here, what this gentleman, Henry Cavendish, did between 1797 to 1799 is do some measurement for those appropriate masses with m1, m2, and r, and f, so that he calculated G like this. These figures are actual figures Henry Cavendish used in his experiments conducted from 1797 to 1799. In this 3-year period, maybe 2-year period, he did all those work, and then 1799 it was published. So m1 is 0.73, m2 is 108.0 kilograms, and r is about 0.230 meters. And I think those are translated into SI units. He may have used pounds and inches and those kind of things. Anyway, he ended up getting this force measurement. And don't pay too much attention to the units unless you're a physics major. Just unit, and then getting this will be complicated enough, because as you can see, 10 to the negative 7th power, whoa, it's outrageous number, outrageously small number. But amazingly, Cavendish calculated all those and then found out capital G. So determine the gravitational constant based upon Cavendish experiment. That's going to be your job. And after that, compare that with, go to Wikipedia or something and get the today's value and compare. If you do it right, you're supposed to get this number. And then today's accepted value is this one. And compare these two. How amazingly accurate for 1797. And even further, here are the mass of the Earth, mass of the Moon, and the distance between Earth and Moon, and we use those to figure out the gravitational force between Earth and Moon. And do your computation. If you do it right, this is what you're going to get based upon Henry Cavendish data, and compare that with today's figure. Again, amazingly accurate. Well, details left to the students. Pretty hard, but it's gonna be worth your time.